Welcome back, students. In this video lecture, we will discuss about cylindrical coordinate systems. In the last video lecture, we have seen about the different vector operations. We have come across how to compute the gradient of a scalar, and we have also seen how to compute the divergence and curl of a vector. And we have done a few problems on gradient, divergence, and also curl. And in this video lecture, I will be discussing about cylindrical coordinate systems. By the end of this lecture, I wish every one of you will be able to convert cylindrical coordinates into rectangular coordinates and rectangular coordinates to cylindrical coordinates. I will start with the basic introduction to cylindrical coordinate system, and next I will move on to the different equations which relate cylindrical and rectangular coordinates. At the starting, as we have already discussed in the previous lectures, cylindrical coordinate system is generally employed to represent cylinder-shaped objects. In electrical engineering, most of the times we will be used to wires, right? Current carrying wires. These current carrying wires, basically they will be of this type, and they will be generally in the form of a cylinder, basically. So that's why we do require this cylindrical coordinate system to represent these wires. And if we take a cylinder, basically as shown in this figure, normally in XYZ coordinate system, we have seen that any point, basically it will be represented in the form of this is XYZ coordinate system, and this is what we call it a cylindrical coordinate system. In the cylindrical coordinate system, we take the base. The base generally will be in the form of a circle. So we take 2 points. One is the center point. We will consider this one here, the center point. We'll take it as an origin, and the distance of the center point to any place on the base, basically it is considered to be, let us suppose this is a base. So any point, it will be in terms of meters or centimeters. So this points of the base, basically they will be represented in terms of r, smaller. I will be employing smaller, which indicates the radius basically, and its maximum value will be minimum, it will be 0, and it may extend up to infinity also. So the basic values of r will be from 0 to infinity. The other one is the z. Now this z indicates it is nothing but the height of the cylinder, the cylindrical view which we are going to consider. So let us suppose if I consider a point here. So this is the radius, and this is r, and this is h. So h will be varying from, it can go in this direction or it can go in this direction. So that's why I'll be considering h from minus infinity to plus infinity. Now we do have another thing, what we call it as phi. Let's take a particular cylinder type object. Basically, let me consider this pen. Basically, now this is a pen. Basically, let us suppose this is the bottom, which is in the form of a cylinder, which is in the form of a circle. Now this bottom, which we are considering as a circle, now I have taken a measure of r, right? And for the vertical dimension, I have taken this measure of h, right? So this is r, this is h, or we call it as z. The other thing is, let us suppose if I choose a point which is on this direction, it is also at a distance of r from the center and at a distance of h from the center regarding the height, right? I can consider the same point on the other direction. Now it is also with r and also z dimensions. Now, but there is a difference between the points if I consider here and if I consider here. So there must be some other component, and that component is nothing but theta, phi, what I am considering here as phi. which indicates, let us suppose if I take this phase as 0 phase, now this phase will be rotating like this. Okay, so it indicates just like an angle which varies from 0 to 2 pi. So that's fine. I am considering a phi which has a values from 0 to 2 pi. So three coordinates are generally employed in order to represent any point in cylindrical coordinate system: r, phi and z. In some textbooks you will refer them as, r is generally referred to as rho, and this phi in some textbooks it is referred to as phi, theta and some other terms. This z is also represented as h also in some textbooks, but we will stick on to r, phi and z. Okay. Now, in the cylindrical coordinate system, see, this is the dimension of r, this is the dimension of theta. So theta, this is just like a plane which will be varying from 0 to 2 pi. Now this is the dimension of r basically, and this is the dimension of z. So z is nothing but an horizontal plane basically, which will be varying from this point up to minus infinity to plus infinity, whereas this will be varying from 0 to 2 pi. And this basically, let us suppose if this is the 0 minimal radius of the cylinder, it will be varying from 0 to infinity. So that's I have mentioned here, r varies from 0 to infinity, phi varies from 0 to 2 pi, and z varies from minus infinity to plus infinity. Now, we can have a quick video on this one. I have taken this video from the internet, and you can see. 1 minute. So cylindrical coordinate system. So this is a representation of r. You can see this is r, this is phi representation, and this is z representation. So z varies from minus infinity to infinity, and r varies from 0 to infinity, and phi angle varies from 0 to 2 pi. So this is the representation of r, phi and z. Okay. Now see, this is a three-dimensional view. Now, having discussed these things, now you will see the conversion between the cylindrical and Cartesian coordinate systems. Now let us suppose we do have these particular points in cylindrical coordinates r, phi and z, and we need to convert them into our regular rectangular coordinates x, y, z. We should employ these formulas. X is equal to r cos phi, y is equal to r sin phi, and z is equal to z. So P is a point which is represented in cylindrical coordinates. Now I am going to convert it into rectangular coordinates. So these are the formula. And similarly, if let us suppose if you do have rectangular coordinates, P in rectangular coordinates, and if you want to convert it into cylindrical coordinates, then you are supposed to employ this formula. R is equal to square root of x square plus y square. Phi is equal to tan inverse of y by x, and the last one is z remains the same in both the things. Now we will apply these particular formulae. Now let us suppose if I do have a point. See, determine the Cartesian coordinates of a point with cylindrical coordinates. 4, 2 pi by 3, minus 2. Now these are cylindrical coordinates r, phi and z. Now let us suppose if I want to compute x is equal to r cos phi. So 4 into cos of 2 pi by 3, it is minus 2. Similarly, y, r into sin phi. I will get 2 root 3. And z is the same, it remains the same, and it will be minus 2. So the new coordinates in rectangular system are minus 2, 2 comma root 3, and minus 2. Similarly, let us suppose if you do have rectangular coordinates. Now these do represent x, y, z. And if you want r, phi, and z. So the first one is r. r is equal to square root of x square plus y square. So first of all, I'm computing r square, and next I'm applying r. And next is, phi is nothing but tan phi is y by z, right? Phi is equal to tan inverse of y by z. Sorry, y by x, right? So I have computed tan phi here, y by x minus 3 by 1, it is minus 3. And phi is tan inverse of minus 3. And one more thing which I am supposed to mention here, see, this is a cos component and this is sine component, right? So if you carefully see, you should be very keen of doing these things. See, this is cos component which is positive and this is sine component which is negative. Now normally if I do tan inverse of minus 3, I will be getting somewhere around 71.56 degrees, right? So I will do just only tan inverse of 3. It is 71.56 degrees, and this 71.56 degrees, what I must do? See, here cos is positive, sine is negative, which means what is a quadrant which I will be considering? So this is both positive, only sine positive, these are both negative, here only cos is positive. So this 71.56 degrees, this, it must lie in fourth quadrant. So that's why I'll be considering it as this one. So normally if I get all positive, I'll consider directly theta. If I get only cos positive, I'll consider minus theta. Or if I get only sine positive, I'll consider like this. If I get, so for tan inverse 3, it is 71.56. Since it lies in fourth quadrant, I am taking it as minus 71.56. Okay. Now, root 10. The z remains the same as phi. Now these are the cylindrical coordinates. Okay. Now moving ahead. This problem you are supposed to solve at your home, or it is a practice. Now I have given you cylindrical coordinates r, phi and z. You are supposed to compute the Cartesian coordinates. And next is, I have given you these things, Cartesian coordinates. You are supposed to convert them into cylindrical coordinates. Now, all these things, what we are doing is nothing but we are converting a point with rectangular coordinates to cylindrical coordinates. Guys, do remember, there is a change basically when you convert points and vectors. Normally, let us suppose in Cartesian coordinate system, if p, x, y, z is a point, normally how will you represent this OP vector? You will represent as xi bar plus yz bar plus, yj bar plus z into k bar, right? Or you will use x, this is u of x, right? This is the representation in Cartesian coordinates. But when you do have this representation does not hold good basically in terms of cylindrical coordinates. So that's why whenever you do have a vectors of this format, let us suppose if you do have a vector of this format, ax into I bar plus ay into j bar plus az into k bar. Okay, I can't directly take it as ax comma ay comma az, and I can directly apply this formula which we have seen in the last class. So those relations which we have done so far, those generally refer to only points but not to vectors basically. So how to convert these vectors into cylindrical format? How to transform these vectors from one coordinate to coordinate system? So this is the formula which we do use. So if I do have this coordinates, if I do have these components ax and ay and az, if you want to convert this into r, phi, z format, then this is the formula. Okay. Now, if you see, if I want, normally in how I must write? AR into R bar plus A phi into phi bar plus AZ into Z bar. This is the representation in terms of. So what is AR? AR is nothing but This is the formula which we will be applying. We will be writing ax, ay, and az, and this is cos phi, sin phi, and 0. So like this, I am gonna do these things. Okay. So we will practice these problems in the class today. But as of now, you are supposed to remember this particular formula, this particular matrix for me. Okay. And next is differential elements. Let us suppose I do have a cylinder. I want to have only a small length across this. Let us suppose if I want to have only small differential length of the cylinder. I don't want to consider entire cylinder. I just want to consider only small length of the cylinder. Now this small length of a cylinder, in which direction I am going to consider? I do have three directions for a cylinder, right? I do have R direction, I do have phi direction, I do have Z direction. So if I do want to consider in R direction, that small length is considered as dr. In terms of Z, it is also dz. But remember, phi is an angle, not a length. So that's why I'll consider it as R d phi. Okay. So these are the differential length, the small portion in length in R direction, phi direction, and Z direction. If I want to complete all these things, if I want to have all these directions, then automatically I'll consider it as dr into R bar plus R d phi into phi bar plus dz into Z bar. The magnitude of this, we already know that dr square plus R d phi whole square plus dz whole square. This is the differential length. Now let us suppose if I want to consider in two-dimensional. In two-dimensional means out of these three, I should consider two things, right? So either I go with these two. So if I take a constant z value, let us suppose if I take a constant z, what I call it as a height, then automatically what will be the surface? The surface will be in the form of a circle, right? So if I consider a constant z, then the circle will be in the form of, it will be having two dimensions now, which can be varying. One is radius, the other one will be angle. So for radius, dr, and this is for R d phi. So dr, and this is R d phi. Similarly, if I want to consider angle, the other two variations will be, one is dr, the other one will be dz. See, dr, dz for angle variation. For z variation, it will be dr and R d phi. Yeah. For R variation, it will be these two, R d phi into dz. So this is for two-dimensional variation. Now let us suppose for differential volume, if I want to consider in this entire volume, I want to consider this particular volume. Okay, small volume. Then I should consider all these things, dr, R d phi and dz. dr, R d phi and dz. Just I have rearranged these things. This is regarding the differential elements. Okay. You should remember these differential elements. Why these are so much important? That we will see in today's class. Okay. And coming to the conclusions, as already been said, this is the representation, and these are the minimum values of minimum and maximum values of cylindrical coordinate systems. Okay. So I hope now you are able to convert from cylindrical to rectangular coordinates, particularly for the points which have been given, and you are able to convert from rectangular to cylindrical coordinates. Thank you.